Hello friends, welcome to another lecture of classical mechanics. Here we're going to discuss about conservation of energy, okay, and Jacobi's integral. Right. So before we start, please subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you. And if you want to follow me on Insta, this is my Insta ID. That is Oza Loikhajit. L-A-K-H-Y-J-I-T Loikhajit 123. So this is the Insta ID. If you want to follow me, then you can follow me. Right. So now let's start. First, let us discuss about the conditions to be fulfilled. Okay. For a system to be conservative, a system to be conservative. So first, the potential must be function of coordinates only. That means they're not the function of velocities, right? And next one, the constraints, right? The constraints are independent of time. They must be independent of time. That means equations of transformation, that is Ri, which is function of q1, q2, and qn, so on, dot dot dot, to generalized coordinates. Okay, transformations from the coordinates r to the generalized coordinate q do not involve time explicitly, right? And hence this Lagrangian L can be written as a function of qj and qj dot, right? So these are the situations, these are the conditions when we can say a system of interest is conservative, right? So now let's go to the next page. The the total derivative of the Lagrangian, in our case, which is a function of position and velocity, here qj and qj dot, is given by dl by dt and summation j del l by del qj, then dqj dt minus, sorry, not minus, plus summation again del l by del qj dot dqj dot by dt, right? So now from the equation of Lagrangian equation, from the Lagrangian equation of motion, let it be equation number 1. Lagrangian equation of motion is this, right? This is the Lagrangian equation of motion. Let this equation be 2. This implies this one, and let it be 2. This is equation number 2. So if we use equation number 2 in 1, then what we're gonna have here, you see. So we're gonna replace this term, right, by this one here, and then we're gonna have this equation, right? So let me write this one first. So here we're gonna replace this by this. So here what we have done, we have just replaced this by this term. Okay, so here we have got this one, right? So let's go to the next page. Okay, so let's see what we're gonna have. So let me copy this last step and let me paste on the new slide. So this is the last step we have got, so let me write it completely. Okay, so this is what we have got. Now these terms dqj by dt is qj dot. Okay, so instead of this we're gonna write qz dot. Okay, we're gonna write qz dot. So then this above equation can be written in this form, right? It can be written in this form, and here we know the product rule of derivative is this. So here we're gonna take this term as u and v as this. Okay, so here this is the u dash into v, this is v into u dash, right? So that's why we can write derivative of product of these two. Hope you have understood this. compare this term with this, and this second part, this part with this. Okay, and u is nothing but this one, and vu is nothing but this one. So this is your u, this is your u, and this is v, right? So hope you have understood this. So now let me first clean it. Okay, so then what we can write this way. So here we have used the product rule. Okay, so now what we can do, let me write the derivative here. Okay, so for conservative system, this del L, del L by del Q Z dot is nothing but del T by del Q Z dot, which is also equal to the momentum. T is kinetic energy here, so this is equal to the momentum Pj, and here T is the kinetic energy, right? So hope you have understood this. Then what we can write, and remember, for conservative system, this v is not function of velocity. That's why with respect to velocity, if you differentiate it, it's gonna give you 0, right? So hope you have understood this. So now this is del L by del T, right? So here derivative should be written. Okay, so I missed this one, so don't forget it. Okay, so now here you see, from this implies this is equal to 0, right? So now let me copy this and let me go to the next slide. So this is the last step we have got, right? And which implies this. So d by dt is taken common, then we're gonna get this. So here you see, if the derivative of this part is equal to 0, so then it must be constant. That's why its derivative is 0, so that's why it is equal to constant. And this constant is known as Jacobi's integral, J, right? That's what we have got here. So now this is nothing but total energy. This part represents nothing but total energy. Okay, so now as for conservative system, okay, L doesn't depend on time explicitly. If so, then this Hamiltonian is defined as this. That means if L doesn't depend on T, then this is nothing but Hamiltonian. And here we have got this is equal to constant, so we can write constant here. And now this part here you can see this momentum Pj. The momentum Pj can be written as mass into velocity, right? Here qz dot, this is nothing but velocity here. So it implies here you can see we can multiply the numerator and denominator both by 2. That means you can simply write 2 into half, then it's gonna cancel again 2. So then you can write this square. So what we have done, we have multiplied 2 and divided by 2. That's it. That's what we have got here. So hope you have understood this. So then this part, half, this is of this form. You can compare with this half mv square, which is nothing but kinetic energy, right? So 2 into T. So this part is T, right? Kinetic energy. So here now we're gonna use this. So here T is the kinetic energy, right? So this is suppose equation number 3, and 2T. This part we have got, this part is equal to 2T, and let us use this one here. We can replace this term by 2T, and doing so, what we're gonna have, let me go to the next slide. So equation 3 implies this after substitution. This is equal to constant, and let's put the Lagrangian, which is T minus V. L is T minus V, and this implies T plus V, right? So which gives the total energy, kinetic energy plus potential energy. T plus V is the total energy, and we have already got that H is conserved, so constant. So that's why total energy is conserved. So as T doesn't depend on L explicitly, and generalized coordinate, generalized momentum conjugate to the cyclic coordinate qj, if this is cyclic and this is conserved. Okay, then equation 2, that you have the equation, Lagrangian's equation of motion, that is the dt of del L by del qj dot minus del L by del qj is equal to 0. If qj is cyclic, then this part going to be equal to 0. Then this equation implies this reduced to this form, right? And we know that this part is nothing but momentum pj, so that's why we can write this is time derivative of pj is equal to 0. If that is the case, if time derivative, if the derivative of pj with respect to time t is 0, then this is constant, pj is constant. As pj is constant, when when we differentiate pj with respect to t, we have got time, we have got 0. So that's why this energy is nothing but essentially the generalized momentum which is conjugate to time, right? So hope you have understood this. Thank you for watching. See you in the next video. So if you have understood, please hit the thumbs up button and share with your friends. Inspire me to create new contents for you. Thank you.